Alexander Bina here, and today's episode will be about chirality and isomers. So this is the concept map. It's actually a summary about chirality. What is it all about? In this entire presentation, we'll be looking into the different elements of this concept along with their examples. So what is chirality? So chirality is also known as molecule-handedness. In other words, it has a left hand and a right hand. Or a molecule can be a left-handed or a right-handed molecule. A molecule is chiral if its two mirror images are not superimposable in the three-dimensional space, such as the two molecular structure that you see in the screen. Supposing if we bring the molecular structure in the left over to the right, therefore this cannot be made to cover the molecular structure on the right. In other words, it will overlap. So what is the meaning of the word chiral? Chiral is actually a Greek word that means hands. Chirality most often occurs in molecules that contain carbon that is attached to four different groups. In this case, we see that the carbon at the center is connected to the group COOH and the R group and the amino group and hydrogen. That is also the same in the other side. Left-handed molecule. An example to a left-handed molecule are most of the amino acids. So amino acids are mostly found to be left-handed in nature. So this now is an example of an L-amino acid. An L-amino acid is a left-handed molecule because you see the amino group is located towards the left. Amino acids are the building blocks of protein. They contain the carboxylic group and the amino group. So this is an example of a left-handed molecule. Now, how about the right-handed molecules? An example to these right-handed molecules are mostly the naturally occurring monosaccharides. So an example to this one are the monosaccharides that are the sugars. Specifically here, we have the D-glyceraldehyde. It is a right-handed molecule because you see that the OH is located towards the right. So these are samples of a right-handed molecule. In nature, left-handed molecules and right-handed molecules of the same molecular structure are mirror images, or they are mirror images of each other, and therefore they reflect image in their molecular structure. So here is an example to that. We have the molecular structure here in A, and the opposite one is called the mirror image. So you see that the hydrogen is still there. It mirrors the hydrogen over there, and this one is the fluorine atom. Then it is mirrored by the fluorine atom over here, and we have the chlorine atom and the chlorine atom also in here, while the bromine is located at the rear side. We also have the bromine mirror image in here. However, if we rotate this object about 180 degrees in rotation, it will produce a non-superimposable image, because if we are going to bring this molecular structure into this one, then we will be not able to allow fluorine and chlorine to fit. That is an example of an image that is non-superimposable. So it means that in nature, there are molecular structures having the same numbers of molecules, but they are oriented in a different arrangement, such as the two. However, even though some of these molecular structure possesses mirror image relationship with each other, they can be non-superimposable or superimposable. Look at the two bottles here and mirror at the center. This left hand bottle is actually mirrored by the right hand bottle. And since this is a mirror image, when we allow the left hand bottle to be on top of the right, or vice versa, the right hand bottle to be on top of the left, they will still produce the same image. So a molecule or object that is superimposable on their mirror images is said to be a chiral. In a chiral molecule, carbon atoms contain at least two same molecules on their hand, so that when we allow them to superimpose to each other, they will exactly fit to the original image. These superimposable molecules are known to be as achiral molecules. So again, this is an example of an achiral object, that they have the same figure when they are superimposed. So the same with this molecule, they can be called a chiral carbon because they can be superimposed. The best way to analyze superimposable molecules is through their plane of symmetry, wherein one side of the molecule from the plane of symmetry is exactly the same or symmetrical in the other side. Now this is the plane of symmetry, and you see that in this plane of symmetry you can find a hydrogen over there, and in the opposite side it is also hydrogen. Therefore, if the same molecular structure will be superimposed into the same structure, it will be an achiral molecule. Look at the plane symmetry of this object also. It has the molecule of carbon and COOH and H and HO on one side. The same also here, it has COOH and H and HO on the other side. So mean to say that if we are going to put this on top of each other, even if we turn it the other way around, it will still produce the same mirror image that can be superimposed to the other molecule. For those molecules that are mirror image, however, are non-superimposable, such as the left hand and the right hand, which is actually the introduction of our topic of chirality. So they cannot be superimposed because the right thumb will be located in the right, while the left thumb will be located in the left. So that is the meaning or basic assumption of the non-superimposable images. These type of non-superimposable molecules are known to be chiral molecules. So again, this is an example of a chiral molecule or chiral object. So non-superimposable, also known as chiral molecules, are called stereoisomers. So what therefore are stereoisomers? So before we go into the details of stereoisomerism, we have to look at the greater umbrella, which is isomers. So when we talk about isomers, these are basically molecules of having the same formula, but they are of different compounds. One type of an isomer is called constitutional isomers. They are also known as structural isomers. This type of isomer, which is constitutional isomer, have basically the same formula, the same number of carbons and the same number of hydrogens, but are structurally connected differently. So again, constitutional isomers are also known as structural isomers. So we have here an example of structural isomers, the butane and isobutane. Now, the molecules, they have the same carbon skeleton, alright? So with butane and isobutane, but the molecules have the same functional group such as the CH, okay? The CH. But the functional group here in butane and isobutane is that they are located in different positions. So what does this mean? That for structural isomer, they can have similar chemical properties, but they have different physical properties. For example, that they will differ in terms of the melting point or the boiling point. Now we move on to another type of isomer, which is called stereoisomer. So what's the difference and similarities between stereoisomer from a constitutional isomer? Stereoisomer, like constitutional isomer, they have the same formula, the same number of carbons, the same number of hydrogen. However, they differ in terms of the connectivity. While constitutional isomerism differ in connectivity of this arrangement of the structure of carbons and hydrogens, in stereoisomerism or stereoisomers, they have the same connectivity. However, they differ in arrangement, in the positionings and configuration of the connections. That is why stereoisomers is also known as spatial isomer, because they differ in their arrangements in space. Now here are some examples of stereoisomerisms. You see that like the structural isomer, they have the same molecular formula, the same connectivity. For example, CH3, this one also has the same CH3, and that one CH3 is attached here and the other CH3 is also attached in here. But it says here that they have the same constitutional isomer, meaning the same formula, the same structure, but the problem is that they have different spatial orientation of the bonds, such as the CH3 in here, unlike the other one that is located in here. So later on we will be understanding the meaning of the cis and trans configuration. The same also with this structure. Look at the difference in terms of the arrangement of the molecules. So now let us look deeper into the characteristics of stereoisomerism or stereoisomer. Okay, stereoisomers also contains chiral centers. Chiral centers, or carbons that are found at the centers, is also known as stereocenters. So these are carbons that are found at the center. Now, how are we going to identify this chiral center or stereocenter? One way to look at it is a carbon that is tetrahedral. Tetrahedral meaning all of the bonds of carbon, the available 4 bonds, are utilized, and these molecules or this carbon is attached to 4 other different either elements or groups. So this is probably a chiral or a stereocenter. And when we speak about chiral center, take a look at the molecules here and the molecules here. So they are well arranged in such a way that we can find all the different chiral molecules or chiral carbons. So wherever a point in a molecule where there are different 4 different groups or different atoms or 4 different atoms are attached to a carbon, that is called a chiral center. So these red dots here represents the chiral center. Now if this is the carbon, it is connected to a bond in here, that's the first, connected to a bond in here, that's the second bond, connected to another bond in here, that's the third, and another bond in there. So that's the fourth. So it is a tetrahedral bond. Now another one is this carbon over here is also connected to that bond. 1, 2, 3, and 4 bonds. That's another chiral center. This one also 1, 2, 3, 4 bonds, and so on and so forth. Now another characteristics of a stereoisomer is that it can be drawn with a Fischers projection. There are many molecules such as sugars and amino acids, and these molecules have more than one chiral atom. So the best and effective way to present this structure with more than one chiral or carbon atom can be the Fischers projection or the use of Fischers projection. Fischers projection is developed by Emil Fischer. Emil Fischer originally used this type of presentation of this type of molecule to show the molecules of amino acids and carbohydrates. And so what are the different lines that constructs Fischers projection? We have the lines that are intersecting to each other, or the intersection line. This intersection just simply represents where the chiral center is found, or the intersection represents the chirality or stereocenter. Supposing this is the molecule, at the middle is said to be the chiral center. So this is the chiral center, meaning to say that the cross section is actually the chiral center. The other line in the Fischers projection is the horizontal line. This individual horizontal line is simply telling us that the direction of these molecules that are attached to the chiral center is directed towards the viewer. Now again, the horizontal line is directed towards the viewer. In this case, our letter C is the molecule that is directed towards the viewer. So again, this solid line here is letter C. It is directed towards the viewer. And another line, letter D, on the opposite of letter C, which is again still going towards the viewer. So they are both represented, the C and D, by the horizontal lines. And finally, the vertical line in the Fischers projection is simply telling us that any attached group or element from the chiral center is directed towards the screen or the page. So the vertical line such as A and B, that is also represented by the broken line in here, A and B are both directed away from the viewer. So they can be projected as the vertical line in a Fischers projection. So if we look at this molecular structure in here, the B and the A is directed away from the viewer or towards the screen or the page. Now stereoisomers have different types. The first type that we are going to talk about here is enantiomers. Enantiomers are actually stereoisomers that have the mirror image relationship. However, they are not superimposable. And so we are going to look at the different types of enantiomers. So here are some molecular structures of an enantiomers. Enantiomers are actually chiral molecules that are mirror image of each other. However, we cannot superimpose these two images because the chlorine atom is projected towards the viewer while the other chlorine atom is projected away from the viewer. So the two types of enantiomers are the D and L enantiomers. This is actually developed by Fischer, and the D and L enantiomers are usually found in carbohydrates and amino acids. So the OH here is what makes these trios called the D trios, because they are projected towards the right, and all enantiomers that are projected towards the right because of this OH, they are considered to be D enantiomers. And so this is the L enantiomer. Now the L enantiomer, such as this one, the OH is towards the left, and the L erythros is also the HO or OH is towards the left. So these are examples of L enantiomers. Now, how can one be able to identify whether it's a D or an L enantiomer? To find this out, one has to simply look at the second to the last chiral center carbon, wherever the group is attached. And so from there, you can determine the L or the D, wherever it is located. Is it in the right or in the left? So it is very helpful to count the second to the last chiral carbon to locate the L or D enantiomers. So we have the second to the last carbon, which is this one, and this second to the last carbon has the OH attached, and the OH is towards the left. Therefore, we can identify that this is a type of L enantiomers. So also this one. And for the D enantiomer, we again will have to count the second to the last carbon, which is this one. So the OH is located at the right. Therefore, this is called a D enantiomers. So here is an example of an L erythros, L trios, D trios, and D erythros. So these are all enantiomers. Now, as a review, since they are all enantiomers, they are all images to each other. They have image relationship. For example, this L erythros is a mirror image of this D erythros. However, if we twist 180 degrees the L erythros, they cannot superimpose to the image of the D erythros. Also with the L trios and the D trios. Therefore, all of these are called enantiomers. Now, another type of stereoisomer is a diastereomer. A diastereomer is not a mirror image like enantiomer, but it usually has two or more chiral carbon, and the geometrical shape has both cis and trans, which I am going to present later. So again, diastereomers are not mirror image. They do not have that relationship. So we have here two example images of molecular structure about diastereomers, and we see that in this molecular structure, compared to this molecular structure, the CH is located at the bottom, and the CH is also located in the other structure on top. So therefore, this is a trans configuration and the other one is a cis configuration, and the two molecular structures are both not mirror images. So that's why they are called diastereomers. And the other structure is that one HO is located away from the viewer, while the other HO is located towards the viewer. So this is called a trans diastereomer, while the other molecular structure, almost the same configuration, but the HO is located, both HO are located towards the viewer compared to the other structure. So they are not of the mirror image relationship. These are what we call diastereomer molecules. An example to a diastereomer is an alkene. Usually, alkene has a double bond. So, alkenes are actually hydrocarbons. When we speak of hydrocarbons, these are hydrogen and carbon molecules. And at least they have one double bond. So for example, this is a double bond of carbon, another double bond of carbon, and another double bond of carbon. And both will end with ene, such as if there are 2 carbons, it's called ethene. If there are 3 carbons, it's called propene. And if there are 4 carbons, it's called butene, and so on and so forth. So here are the 2 geometric shape of a diastereomer. One is cis, which means it is found in the same side. So an alkene will have a configuration of cis. In other words, that the groups attached or are found on the same side of the double band. So these are the double band, and the 2 groups are attached on the same side. So this is called the cis. While the 2 hydrogen also are found on the same side. So this is called a cis configuration. And the other one is called trans. Then they are found in the opposite sides. So compared to the cis, this trans 2-butane will have a configuration which their attached groups are in the opposite sides. So the CH group is found at the bottom, while in the other side, the CH group is also found opposite to the bottom, which is on top. While the same happens to their hydrogen atoms, they are also found in the opposite side. So anything that same group are found on the opposite side, they are called the trans configuration. Diastereomers are chiral molecules. They are called chiral molecule because they have the chiral center. Their chiral center will actually determine the number of probability of forms that can be made out from the molecule of a diastereomer. This will be basing from the formula 2 raised to the power of n, where n is the number of chiral centers. Now supposing you see a molecule of diastereomer and you find out that there are 3 chiral centers, such as 1 chiral center, 2 chiral centers, 3 chiral centers, and there are different R groups attached. We will name them as 2R, 3R, and 4R. So these are the different groups that are attached to our chiral centers. Now, what will be the possible number of forms that this type of combination of diastereomer can have? The formula is 2 raised to the power of n, where n here is the number of chiral centers. And since there are 3 chiral centers, this will become 2 raised to the power of 3. And the possible total outcome of this combination of this diastereomer is a total of 8 combinations or forms. So we have this first, which is an enantiomer. All chiral centers are of opposite configuration. So we will now have the 2s, 3s, 4s. So 2s, 3s, and 4s, that will be in the opposite side. And the original one, which is at the 2r, 3r, 4r, which is in the original position, while there can have 2r and 3s and 4s will be in the opposite side, where we can also have 2r and 4r both in the original position, while 3s will be in the opposite side. And another one is that we can have 2r, 3r in the original position, and 4s will be in the opposite side, and so on and so forth. So this is the beauty of using this formula, and that is how the biological molecule becomes abundant in our body because of this possible combination. For example, if there is one molecule or a group that is attached differently in one configuration of one carbon atom, this is called an epimer. So an epimer actually occurs when, for example, there is one chiral, such as the third to the last or third from the last carbon center has a configuration of OH, and the other one is in the opposite configuration. So both the OH are located at the right in this configuration, while the other OH is twisted to the other side, which is at the left. So there is one chiral centers with a different configuration, and this will now become an epimer. So it's a diastereomer that has a different configuration of the OH. So it is a diastereomer that is also specifically an epimer. So these are all the different conceptual summary about the lesson chirality and isomerism. So again, when we speak about chirality, this is also known as the molecular handedness, where there are two forms, the left-handed, and most of the examples of left-handed molecules are amino acids, and there is also a form of right-handed molecules, and most of the form of it are naturally occurring monosaccharides. So the left-handed and the right-handed are actually the mirror image of each other, where even though they are mirror images, there can be a non-superimposable or a superimposable images. And when we speak of a superimposable images, those are chiral molecules that are called a chiral molecule. So chirality, that is called a chiral molecule. And when we speak of chiral or a chiral molecule, it has a plane of symmetry that where we are going to examine in such a way that they are really symmetrical, that when we put one molecule on top of each other becomes a superimposable image, while the other non-superimposable image are called chiral molecules, and these are also called stereoisomers. And so when we speak of stereoisomers, so when we talk about stereoisomer, we have to go back to the original idea about isomerism. And isomerism is actually, they have the same formula but they have different compounds. And talking about isomers, there are two types of isomers. One is constitutional isomers, or also known as structural isomer. They have the same formula but they are connected differently. However, in type of isomer, which is a stereoisomer, they have the same formula, they are connected in the same structure, but the thing is that they are oriented differently in space. That's why it's called spatial isomer. This actually type of isomer can be drawn using a Fischers projection. Then in a Fischers projection, we have to consider the different components of a Fischer projection. These are different lines, that the intersecting line are actually where we can find the chiral center, while the lines that are horizontal are actually the components or groups that are attached to the chiral center that is projected towards the viewer, while the vertical line is the opposite of the horizontal line, that are the attached group or individual elements that are actually connected to the chiral center, moving away from the viewer or going into the screen or the page. And so when we speak of stereoisomer, this contains chiral centers. These are also known as stereocenters. And the only way to determine a stereocenter is through the type of carbon that has a tetrahedral molecules attached to it, or the elements that are attached to one carbon. And so going back to stereoisomerism, there are two types. The first type is enantiomers. These are mirror images of these molecules, but they are non-superimposable. And an example, or there are two types of enantiomers. These are the D enantiomers and the L enantiomers. And when we speak of L enantiomers, is that we can find the OH in the left side of the molecular structure, while in the D enantiomers that we can find the OH in the right side of the molecular structure. And it's so easy to determine whether it's a D or L because we have to examine the molecules of the molecular structure from the second to the last carbon where the OH is located. So that's how easy it is to find the D and L configuration of an enantiomer. And talking of the other type of stereoisomerism is called diastereomer. And diastereomer, example to this are the alkenes. And alkenes have the configuration or notation of the cis and trans notation. When we speak of cis, that all the group attached to the double bond carbon are located in the same side, while all the groups that are located in a trans configuration are located in the opposite sides. So that's how to look at the diastereomer. While in diastereomers, these are actually not mirror image, or they do not have the mirror image relationship of these different molecular structure. However, they are both chiral molecule. They have chiral centers wherein there are different groups attached to the same chiral center but in the opposite side, for example, and that is a special type of diastereomer called Epimer. And this chiral center, by the way, is the one that we can determine the number of possible combinations or forms of our diastereomer by just using the formula 2 raised to the power of n, where n is the number of chiral centers. And so that's it. I hope that you enjoyed this very simple conceptual summary about chirality and isomerism.